Hi, this video is all about the relationship between mountains and oceans and the climates that they help to create, and particularly linking them to plate tectonic changes. Here we can see a graph of ocean temperature from high latitude southern oceans running through the Cainozoic era. If we look at this graph, we can see fairly clearly a long-term trend of changing climate. This information is derived from oxygen isotopes found in microfossils in ocean sediments. So we can be pretty confident about the reliability of this data. You can see we're looking at a significant drop in surface water temperatures over time. We need to consider why this may have occurred, and in particular to think about the rates at which it occurred. If we look at a paleogeographic map from the late Cretaceous, we can see that Pangaea is still slowly being pulled apart. Africa and South America have separated in the early parts of the South Atlantic Ocean. Northern Europe, though, and North America are still fairly firmly close together. And we're starting to see the separation of the southern continents. Note the position of India as well. As we move forward in time into the late Eocene, part of the Paleogene period, we can see the Atlantic starting to open further north. There's still circulation of oceans between India and Eurasia, between Africa and Eurasia, and also between North and South America. Some 20 million years later, in the early Miocene, there's been significant change. We have what's now the Mediterranean Sea been formed. India has collided with Eurasia. Australia has completely separated. And crucially, you can see Antarctica having moved further south, starting to cover the southern polar regions. The circulation of the oceans, shown by these arrows, though, has changed markedly, and with it the distribution of heat from the tropics to the poles, and vice versa. If we look at the circulation patterns today, we can see they're very different. The biggest change we see between this and 20 million years previously is that now North America and South America have joined in the isthmus of land in Central America, separating largely the oceans of the Atlantic and the Pacific. Also notice that Antarctica is separated from South America. How does this affect heat transfer? How does this affect heat going from the equator to the poles? Particularly if we look at the oceanic circulation patterns in the southern oceans. Okay, let's focus in on a small part of this. This part of the ocean between the southern tip of South America and the northern tip of Antarctica, called the Antarctic Peninsula, is a fairly recent feature. You can see from this diagram that 43 million years ago, these two landmasses were almost joined. There's a slight separation by 32 million years ago, but by 25 million years ago, that really hadn't progressed very much. It's only 10 million years ago when plate tectonics pulls these two landmasses apart and allows for the circulation of significant quantities of very cold polar waters. This must have a big effect on climates. If we look at the situation at present, this diagram shows us the depth of water that exists between these two landmasses. You can see we've got some very deep ocean in between the two landmasses now. Yet this is a relatively recent geological feature. The impact of this on temperature is stark. You can see the graph at the top of this diagram showing a significant jump in temperature as we get to the polar front, this boundary between warmer and colder water that circulates around Antarctica. There's also a corresponding change in salinity of the water as well. Now, we saw on the previous diagram that this happens about 10 million years ago. Go back to your graph, mark a line at 10 million years, and see what impact that the opening of this Drake Passage had on global climates. Well, in particular on the temperature of the southern oceans, but the impact that that can have then on global climates. This must be a significant event in the cooling of global temperatures during the Cenozoic. Another significant event that happened during the Cenozoic is the Himalayan Orogeny. If you remember the diagrams that we looked at earlier, looking at the plate tectonic evolution of the world through the Cenozoic, we saw the very rapid northward movement of India. That rapid movement, crashing the two continental zones together, has created the biggest mountains in the world. It was moving about 9 meters a century, very, very rapidly for a plate. When it collided between 40 and 50 million years ago, that slowed down, but the impact that had on pushing up this huge barrier across the continent changed the circulation of air from tropical regions in the Indian Ocean to northern Asia. The impact that had on climate was profound. We see areas to the south that's affected by monsoons, these very heavy seasonal rainfalls, may even have contributed to the cooling of the earth in the Quaternary with this reduction of heat transfer from the tropics to higher latitudes. If we have a look at a map of the region today, we can see the effect of the orogeny very clearly. India is largely low-lying, but its northern edge, including that of Pakistan and Bangladesh as well, is marked by this ring of mountains, this immense barrier to the warm, moist air coming off the Indian Ocean and the Bay of Bengal, moving north and hitting that barrier of the Himalayas, keeping that warm, moist air above India and Pakistan and Bangladesh, and preventing it going further north into Tibet and China. We also have the Tibetan Plateau, an enormous high altitude area that in many places has a desert-like climate. If we pick two places to illustrate the differences and the effect that the Himalayas have, if we look at the capital of Bangladesh, Dhaka, and compare it with the capital of Tibet in Lhasa, these two places are only 660 kilometres apart. The distance may be from Cardiff to Glasgow. Yet there is a major difference in the climate of these two places. Dhaka has an average daily temperature of over 26 degrees, an average annual rainfall of comfortably over 2 metres. Lhasa has an average daily temperature of only 8.8 degrees, with average annual rainfall of less than half a metre. You can compare that with a typical British city such as Cardiff. 11 degrees daily temperature, rainfall of 1,152 millimetres. The reason, though, for the difference between Dhaka and Lhasa is this Himalayan barrier. Before those mountains rose, that heat that is trapped across the Indian subcontinent would have been transferred further north. The moisture that falls in such abundance in the Indian subcontinent would also have travelled further north. This would have had a huge impact on the climate. So, to conclude, changing patterns of circulation of these global commons, the oceans and the atmosphere, have a profound effect on climates around the world. This is because it controls the distribution of heat, the movement of heat from the equator to higher latitudes. Now, this can only be part of the explanation for climate change in the Quaternary. It establishes long-term trends, not necessarily the short-term variations and, crucially, the fluctuations that we see in Quaternary climates. To explain those, we need to find an additional mechanism. More of that later. Anyway, don't forget to come up with your interesting question and bring it along to class. I'll see you then.